Hello guys, welcome to another video. This one is going to be based on a physics topic known as the electrostatic force. You'll typically see this first in a course on Physics 2. And so the electrostatic force it deals with charged particles. And just like the mechanical forces produce kinetic and potential energy, electric forces can transfer electrical energy. And so that is the whole reason why we are studying this. So here I have two charged particles. All right, let's just call them Q1 and Q2. And they're separated by a distance of r. And so what we can write about the forces that are being exerted on each of these particles is that it is equal to the product of the two charges divided by the distance between them squared multiplied by a proportionality constant k. It is important to note what the units are here. So F is going to be in newtons, just like it was in Physics 1. Q1 and Q2 are in units of coulombs, and we'll talk about that unit here in a moment. And then R is going to be measured in meters. The proportionality constant here is this huge number, 9 times 10 to the 9 Newton times meter squared per coulomb squared. So if the signs of Q1 and Q2 are the same, that means that the force between them will be repulsive. So you'll have two particles, and let's say they're being held in place or something. They're being like held in place by a machine. We have Q1, Q2, and let's say they're both protons, so they both have positive charges. Well, this means that because their charges are the same, that these are going to repel each other. So the force of Q2 on Q1 is going to act to the left, and then the force from Q1 on Q2 is going to act to the right. And so that's a repulsive force. However, if the signs are opposite, so let's say you have like a proton and an electron, right? So then we've got our positively charged proton in some vicinity of our negatively charged electron, and we'll actually take a look at this in a second as well, more detail, separated by this distance r. The force here is going to be, so if this is 1 and this is 2, the force from 2 on 1 is going to be basically in this direction. So the force, it's going to go to the right. And then the force of 1 on 2 is going to pull it to the left. So they're attracted. The force is attractive when the signs of Q1 and Q2 are opposite. All right, let's talk about what is going on with the magnitude of the electric force. That constant K being 9 times 10 to the 9 should raise a pretty big red flag. We'll just start with an example here. So we've got two 1 coulomb charges, Q1 and Q2, and they're just separated by a distance of 1 meter. 1 coulomb, 1 coulomb. We're not saying what the sign is, so I'm just going to assume they're both positive. It doesn't matter in this example. And separated by a distance r, we have to determine the force. And so by just plugging in all these values, we see that the force from just two charges that are 1 coulomb apiece and only 1 meter apart that results in a force of 9 times 10 to the 9 newtons. Now, let's compare this to the gravitational force. So compare to the gravitational force. By finding something, well, let's find out what kind of mass would cause that same gravitational force. That's what we're going to do right now. What mass is going to cause the same gravitational force? Remember, this is the electric force. Note the subscript E right there. So if we use the form Fg equals ma, we can find the mass by just saying that m equals Fg over a. And a in this case is going to be our g, which is 9.81. So when we plug those values in after flipping it around algebraically, we get the mass is equal to the force that we got in the previous calculation, but now we're substituting that in for the gravitational force, and then we're dividing by the acceleration of gravity on Earth, and we get 9 times 10 to the 8 kilograms, which you can do a Google search, like what kind of things weigh that much. Like an industrial forklift weighs that much, right? And also like large cranes used in high-rise building construction and things like that have a mass on the order of this magnitude. And so remember, we got that force from just using 1 Coulomb charges that were just separated by 1 meter. So this tells us that the Coulomb unit is huge. It's a huge unit. But that's okay. That's fine, because the devices that we use in like our appliances and just household things in everyday life, they only range from like the nano to millicoulomb range. So we don't have these like huge forces constantly around us all the time in our devices. They engineer that for safety of a laboratory and things of that nature, so that we can safely work with these things, work with these devices, and use them to our advantage. However, we can get really high electrostatic charge from nature. Nature does not seem to care about the engineering safety of our world, our human existence. And so the electrostatic charge buildups between the Earth and the clouds can get up to 10 to 15 coulombs. And that is much higher force attributed to that electrostatic discharge event. And you can actually tell by the sound of the lightning when it cracks, and it can break trees and do all sorts of stuff. So the forces attributed to those types of electric forces in nature is actually astronomical compared to the things that we deal with in our everyday life. I want to draw an analogy between the electrostatic and gravitational realm. So we can see the similarities between these two equations right away, these two relationships that define our gravitational force and our electric force. Now, both of these relationships contain a factor of 1 over r squared. This kind of allows us to do a little quick trick, like so. Let's say if the distance between these two objects is doubled, so if r is times 2, that indicates that the force is going to be divided by 4. Similarly, we have if the distance is multiplied by 3 between these particles, then the force will be divided by 9. So that will help us a lot in a future calculation that we'll be doing with vectors. So we also notice there's a product of the two intrinsic properties of each of the particles involved in this interaction. In the gravitational force, it's going to be mass, and in the electric force, it's going to be charge. And we also have a constant of proportionality in each one, right? And we kind of already know the values of these. We have the capital G is very small, but the lowercase k is huge. And so that gives us intuition about the relative strength of these forces in the universe. Now, so these analogs can be drawn. It's sort of a duality between the electrostatic and gravitational realms. Is that mass is analogous to charge. The constant G is analogous to the constant K, and then R is analogous to R. However, this isn't totally symmetrical because the gravitational force is only attractive. However, the electric force can be either attractive or repulsive depending on the relationship between the signs of the two particles involved in this force interaction. Now, I want to use the hydrogen atom to compare the forces as well. And I'm just going to list some knowns that have been predetermined by physicists repeatedly in history. So M sub P, this is going to be the mass of the proton. M sub E is going to be the mass of the electron. R is the distance between the proton and the first valence shell of this hydrogen atom. Let me write that here. This is a hydrogen atom. And if you've taken chemistry, you would know that right away because it's just a proton with one orbiting electron negatively charged. All right, so what we're going to do is we're going to first calculate like what the gravitational force would be between the electron and the proton, which I did right here actually, by just plugging in the G m1 m2 divided by r squared. That's what this is. And then I also did the same thing for the electric force, but obviously we're doing our electric force formula here. And so essentially what we got going on here is that when we do the gravitational calculation, we get this tiny 3.6 times 10 to the negative 47 newtons. That's essentially not detectable by anything. And therefore, it is probably not the thing that is primarily responsible for holding the structure of the atom together. But when we do the electrical force calculation, and we see, well, what would the electric force between these two be? We end up getting a much larger number. In fact, 10 to the 39 times larger of a number. So what this tells us is the electric force is the force that's responsible for the stability of the atomic structure, because its contribution is so much larger than the contribution would be to the force of gravity due to the mass of these tiny particles. We're talking about protons and electrons, which have these masses that I listed right here. And so that will conclude our first discussion on the electrostatic force. We will delve more deep into how we can apply vector mathematics to determine the forces on systems of charges or that are greater than two particles. And we'll use different charges and different configurations geometrically to analyze the motion of these particles and the forces on them. And if you enjoyed the video, please make sure to like and subscribe. That would help me a lot. Also, leave a comment if there's anything that you want me to clarify, or anything that you would like me to cover in the future, and I will be happy to oblige. Thank you for watching, and I'll see you next time.